So let's discuss buoyancy force. Buoyancy force is a force that is exerted by a liquid or a gas against anything that is inside of the volume of this liquid or gas. So over here we have a beaker. So let's fill the beaker with some liquid. Let's say the liquid fills up here. And at the moment there's nothing other than the liquid itself. So we just imagine there is this volume of liquid. We're just drawing the lines to indicate this volume and just kind of set it aside from the rest of the liquid. So the fact that the liquid can stay in a static equilibrium, that's because every part of the liquid is in equilibrium. They are not really moving around. So this part of the liquid must feel balance of forces. So the downward force is the gravity on this volume, and the upward force is the buoyancy force from the rest of the liquid supporting this liquid volume. And these two forces are equal and opposite, so they balance, and the liquid volume doesn't flow either up or down, causing the whole liquid to move. So this is our assumption. There's a static liquid, or maybe a quasi-static, that is a liquid that doesn't move much. So we have static liquid, and the upward force, buoyancy force, balances the downward force, gravity. So let's calculate these two forces, starting with gravity, which is slightly easier because we don't know what exactly is buoyancy force at this point. So gravity of this volume of water should be mass times gravitational constant. And mass, because we're dealing with liquid, we can use the density of liquid times the volume. Okay, so now we have gravity in volumes, density and volume and gravity, and we typically order the terms this way: rho g times v. So rho is the liquid density, g is gravitational constant, and v is the volume of that liquid. So this is equal to buoyancy force. So we conclude that buoyancy force, let me rewrite that, is equal to liquid density, gravitational constant, and volume. So this means in outer space, when there is no gravity, there's no buoyancy force. Say if you're inside of a liquid, you place something, say metal, inside of a liquid, it will not feel buoyancy force, so it will not have a tendency to move in a certain direction towards, say, the surface of the liquid. And the liquid also doesn't feel volumes like they would do normally on Earth. So if you have some liquid out in outer space, say inside of a space station, it would more or less form a sphere. Probably the surface will vibrate, but it likes to form a sphere instead of feeling a beaker like this. Okay, so back on Earth, we have this as buoyancy force. So how does that help us with other objects that are inside the liquid? Well, because the liquid doesn't really know what's inside the liquid, it'll always support the same amount of volume with the same amount of buoyancy force. So the buoyancy force is dependent on the volume of the object that is submerged. So now let's first just assume that an object is completely submerged. We later can assume there's a partial submersion, so the volume is only the submerged volume. So let's consider buoyancy force of an object, this is, let's say, metal. We have a mass of the metal, which is equal to the density of the metal times its volume. And we'll have an assumption that this density of metal is greater than the density of the liquid, or more or less water, common liquid. So the density is higher, and we'll calculate gravity on the metal, which is density of the metal times its volume, and then times gravitational constant. This turns into rho GV, metal density, and this is greater than this rho liquid GV, right? So what this means is gravity on the metal is greater than buoyancy force provided by the liquid. So in this case, the metal should sink to the bottom. So let's draw the situation right here in this beaker. So we'll have a metal here that is completely submerged. And its gravity is greater than its buoyancy force. So it ends up accelerating downward because of this net force. So this sinks. So it sinks. And what about for something that's lighter, say wood? So we have a mass, and mass of the wood is density of wood times its volume, and the density of wood is less than the density of the liquid, common liquid being water. And gravity on the wood is density of the wood times volume times gravitational constant, which we reorganize the terms, and that's greater than density of the liquid and gravitational constant in V. So in this case, less, because wood density is less than liquid density. So gravitational force is less than buoyancy force. This is flow. So we're assuming in both cases the metal or wood is entirely submerged in water, right? Wood does not want to stay entirely submerged in water, so we're just assuming that it's been pushed inside of the water, so it feels buoyancy force up greater than gravity down, so it will eventually flow up to the top, right? So let's first revisit metal. So metal's gravity is greater than buoyancy force, it'll sink, right? So metal, what happens when it sinks? So this metal sinks to the bottom. So now it sits here, right? It sits here. So we'll have to move the page a little bit to have more space. So it still has its gravity the same. It still has this insufficient amount of buoyancy force. But now, since it's sitting on the bottom, it is receiving some normal force from the bottom. So there's this normal force, N or Fn. And these two forces will balance gravity so that the metal will just sit happily at the bottom of the container, right? So let's say bottom. Bottom of the container. We have, let's write here, gravity down equals buoyancy force up and normal force, right? So we can find out how much normal force is needed. Gravity minus buoyancy, right? Mg minus buoyancy is rho liquid, G times the volume of the metal. So that's how the metal will end up basically sinking to the bottom. And for the wood, say we let go of the wood while it is submerged, the wood will flow to the top. So we'll draw a situation where the wood is flowing to the top, right? So this is a situation. Only part of the wood is still submerged. So let's analyze the forces. We still have gravity, the same amount of gravity, but now we have different amount of buoyancy force because there's nothing else. This is a bit too long. I want to draw about the same length. So buoyancy force on the wood. Now let's say metal. Wood. Okay, buoyancy force on the wood is upward, and it balances gravity on the wood. This is explained by the fact that only this portion of the let's change the color so I can still mark the lengths. So get rid of, oh, that is interesting. Wow. Hopefully I can draw a red over the black. Sometimes it just doesn't like it. Okay, so that's indicating, oh, we have the same exact amount of forces. Oh, look at that, it just went to the bottom. Okay, it doesn't really like how to handle the right layering of strokes. Okay, so what we're seeing here is, because this last amount of submerged volume, this is the total volume that was submerged, right? This is only partial of the volume that gets submerged. So that apparently receives less buoyancy force because buoyancy force here is proportional to the volume submerged, right? So let's use a subscript. This is V submerged. Submerged volume. So now for the wood, we'll have gravity equals buoyancy force. So mg equals this rho liquid g and the v submerged. Okay, so if you change the mass into density of the wood, volume of the wood, gravity, density of liquid, gravity, volume submerged, then if you divide out gravity and you still have the densities, you can say submerged over volume, so you divide volume on both sides, then you get V submerged. Then you divide out the liquid on both sides, you get rid of that density. So now you have this divided by this volume is rho W over rho L, or just percentage of submerged. Let's not use that percentage sign. Let's just use V submerged over the total volume, just to be more clear what that volume is density of wood over density of liquid. So we certainly can use this method to find density, roughly find density, if we find out how much fraction of the wood is above water, so we know how much is below. Right. Thank you.